Hello everyone. Today we will talk about modal analysis. Modal analysis, you have already learned about modal analysis from your course on structural dynamics. Here we will take an example and try to model it using finite element tool Abaqus. That is the idea of this video. So, first of all, we have considered an example from the book by A.K. Chopra. We have considered a two-story frame structure. We can say it's a shear frame because the columns are flexible, but the beams are rigid. And okay, we have given I have marked the dimensions for the column, beam, and the corresponding cross section for the column for the different floors. And what is the value of the corresponding parameters marked here, like A, B, H, and of course the beams are considered to be rigid, and we have considered the lumped masses at different floor levels. The value of the mass are also listed down here. If we use this parameter, then following the book by A.K. Chopra and of course any other book you can follow, then you can it's a two degree of freedom system because only things it is moving, it is only this lumped mass is moving only in the horizontal direction. So, it is a 2 degree of freedom system, and you can write down the stiffness matrix and mass matrix, and from that you can compute the eigenvalues and eigenvectors. Again, eigenvalues is linked to the frequency square, so, like the square of the circular frequency is the eigenvalue, and eigenvector will give you the mode cell. So, after doing this calculation, we can arrive at this results. Okay. Right, and now in the following video, what we will do, we will try to do this problem, to solve this problem, model this problem first in Abaqus, and solve carry out the modal analysis to get this number. All right, let us try to model the problem in Abaqus. So, first thing we need to create a part. Right, it is a 2D planar problem and we like to create some wires. So, let us go ahead. The first trick about modeling is to create some construction lines. And okay, now we should create, all right, let us create some boxes. We are by default assuming the unit system to be followed, Newton millimeter second. So, we will enter everything in millimeter here and see how it is. Okay. Now, create another box starting from there. Sorry. And it will go all the way up to 1000. Alright, let us see how it is. Okay. Now, cut this. So, we already have the geometry. Alright. Now, what we will do? We will create a few sets because we like to apply some boundary condition and other stuff, right. So, we will say fix, and these are my fix, and we will create some bulk for the entire stuff to apply some boundary condition and other thing. Now, all right, what do we like to do now? Okay, we like to create a material property elastic. Young's modulus we have considered to be 200 Newton per millimeter square, and let's keep it 0 because we like to be okay, or otherwise we can enter some value like say 0.3. Right, now we create a section for beam. Okay, now we have different material section for different floors of the column. Okay, let's for floor 1, and for this you may refer to the previous slides I have shown you. There I have mentioned the dimensions, so I'll write on rectangular, and this is for floor 1, and here, okay, this A is in this direction. Okay, anyway, we'll use 100. Okay, and we make a copy of this for floor 2, and we edit it, and floor 2, and we know it is alright. And now we like to assign, okay, oh, sorry, we like to, before assigning anything, we need some more sets. Column 1, and column 2, and we like to assign the properties. We used, okay, column 1, and we use a floor 1, column 2, we use floor 2. Alright, but there are, these portions are left out, right? Let's apply some, okay, I will just say beams, although these will not be used in modeling, but okay, and supply some material property. I'll tell you why, of any value, okay, why it is not being used, because we are going to define this to be rigid. Alright, now what we will do, we have assigned the sections, but we need to define the masses, right? And for this we need to define the masses at the center. So for that we need some point at the center, right? So here, okay, so to do that, how we can do that? Okay, we need to go to special inertia, create point mass or inertia. Now there is a small trick, like we should create a rigid body first, right? Okay, now we go to assembly. and we go to interaction, and we like to create some interaction. So for that we need something more, and this is reference point. Okay, say this is reference point 1, this is reference point 2, and what else will do, create a few sets. Okay, and P1, continue, select this one, and RP2, continue. All right. Okay, you can create inertia from here as well. Inertia 1 in reference point 1. All right, what is the value we expect here? Value of 2000, because m equal 1000. All right, and we say rotary inertia is 0. All right, now we make a copy of this, inertia 2, and we choose this one. All right, same thing, 0, 0, 0. Oh, but we want to apply value of 1000. All right, now we have we have defined the properties, we have defined the mass. What else we need? Okay, we yet to define this beams to be rigid body. For that we need to define a constraint. Okay, so body, and we have already created sets for beam. Say beam 1 means the beam at the floor 1, it is highlighted as you can see, and the reference point is already created it. Okay, and make a copy to make it quick, and edit, and we'll need to modify it to beam 2 and RP2. Okay, so as you can see it is highlighted, right? All right, now test mesh and save. What else we are missing? Okay, we need to define the load, like basically the boundary condition we need to define, and we will define to be fixed. The same thing we can define, like let me delete it and show you alternate ways. You can define to be a regular stuff, like sorry, my mistake. We like to define it where at these 2 points. Oh, there is some problem maybe. Okay, we'll do it. So everything is fixed. Maybe I have not selected it properly. Let me see. Yes. Okay. All right. What I need to do is, okay, this is create. go to load module, sorry, make a copy of this boundary condition 2 and it's fixed. Anyway, so we have defined the boundary condition, we have defined the masses, we have defined the material properties, sectional properties. What we need to do is mesh. Better to do on the part, sheet part. Okay, and mesh part. All right, but we need to do one more thing. We need to assign the sectional orientation, because the section is not symmetric except for the circular section. For any beam we need to define the orientation. Okay, for the entire thing let's choose some orientation and say okay, and to check it you can go to view, part display option, you can render. Okay, let us see how does it look like. All right, because we are, yes, so the idea is the wider part of the section should be in the lateral direction, in the x direction, because we are finally thinking of applying lateral loading. So the section which are asymmetric should have maximum stiffness in the lateral direction, the loading direction, so that we have a overall structural stiffness is maximum for the lateral loading. That is the idea. Anyway, it seems to be fine, because as you can see here. Okay, now we have done our mesh, so let us create a job, say M2 2. Okay, continue. Okay, oh sorry, I need to create a step, right, for the modal analysis. So I'll kill it and I'll go to step module and create a frequency step. Okay, something important here, we like to specify some lower bound and upper bound of the frequency, because it's a numerical solver, Langsos, which is used. So specifying the lower bound and upper bound will help the solver to only to show useful solutions. Okay, how to choose this number? You can have some idea from the analytical solution, like what is your first mode, you can get that from using some thumb rule or some analytical solution for simple problems. And now we have this, and okay, and we can also check this, what are the outputs. Okay, for all mode you can get the mode shapes. Okay, job, now submit it. Okay, job completed successfully. Let us have a look at the results. All right. To understand the modes more clearly, okay, and we choose a uniform deformation. All right. Okay, this is like the initial state, like base state, and this is first mode, and this is second mode, right? All right. So okay, the other modes are not very important. We are interested, okay, because other modes are not okay. To ensure the, let me see the displacement values, horizontal, vertical, there is some vertical displacement. So what do we need to do? Say for example, this beam is supposed to be very rigid, and let's restrain the vertical displacement of these reference points. Then it will show only the mode shape corresponds to horizontal displacement of the frame. Later I will show you through another example that okay, if there is no constant, then what happens, but we like to follow the ideal scenario, follow the example provided in the textbook. So we are doing this, and initial state, continue, reference point 1. What we like to do, we like to restrain the vertical displacement. We do not like to allow any. This, create point 2, continue, no vertical displacement is allowed. Okay, now let's redo the simulation. All right, it is done. So results. Okay, now let us look at the values. Horizontal displacement, vertical displacement, now it is 0, right? Okay, and of course we can see the values. Now let us go to okay, so just have a note of this number, see, and now we will go to the slides to show you the comparison with the analytical solution. Okay, so yeah, we copy pasted the result here. Now have a look here. The frequency, the value means here the eigenvalue. Okay, so eigenvalue is 9.77. Okay, this is actually from from my previous modeling, but you will get a quite similar number. And frequency is 0.49747. And from this analytical calculation, we have a eigenvalue of 10 radian per second and frequency 0.5 cycle per second. So it's very close, right? And the for second problem, second mode, we have a value means eigenvalue omega 2 square is 40 radian per second, analytical calculation, and we are getting around 39. And the corresponding f is frequency, means it's basically in hertz. So it is 0.99 analytically, numerically, and analytically 1 cycle per second. So the numbers are pretty good. Now we will go to Abaqus again to try to do some other cases, like here we have made many assumptions about like rigid body and other things. So and for this idealistic scenario, we could compare our numerical results with the analytical solution and provided in following the textbook example. Now what we will do, we'll remove these assumptions like of this rigid body and use a uniform, use a instead of a lumped masses, we'll use a we'll specify the density of the material, okay, for a realistic scenario. Okay, now let's go back to Abaqus. All right, we are back again to Abaqus modeling. All right, let's go to model, and to make it quick, let us make a copy of this model as model 3. All right, here what do we like to do? What we like to do is, first of all, let's define some density as well. So let us consider a density of, because everything here is in Newton millimeter second. So considering material properties closely corresponds to steel. And now we will remove all the assumptions. Okay, what were our assumptions? For example, we go to interaction module and we do not need this. And what else? We define some lumped masses. Now we are not doing any lumped masses thing. Well, we have defined the density, so Abaqus will automatically compute the mass matrix based on the density provided. And what we need to do is, we defined, yes, masses here, right? What we will do, we will subtract and suppress. Okay, there is no lumped mass now. It is like, as you can see in this this geometry, this is our actual geometry now. Okay, and the structure is fixed at the bottom, and now we are like to compute the modes, say eigenvalues, eigenvectors. So let's create another job. Continue. Okay, you can do data check to see everything is fine, but just you can also submit. It will do data check first, then run the simulation. Let's see how it is going. I see. I defined a few boundary conditions to restrain the vertical displacement of the reference points. No longer it is valid because there is no constraint definition for the rigid body of this. Now it is not a rigid, beams are not rigid, everything is flexible. Now submit it again. Alright, you can always use a monitor and see the progress, but it's a linear simulation. Okay, it is done. Now let's go to the results. Alright, oh, too much of deformation. Okay, let's go one by one. This is the base state, there is nothing, and this is the first mode. Okay, the values are very different than what previously observed because of the changes in the mass, because the mass values are very different now. Okay, this is the first mode, second mode. Okay, at least the mode shapes you can compare, right? The mode shapes are quite similar first two modes, but of course there is a deformation here. And but yes, you will observe other modes, right? Other modes because of the deformation flexibility of these members. So these are all different mode shapes and the corresponding eigenvalues are also given. Okay, now for this problem, calculating analytically is very difficult, right? As you can understand, we cannot do analytical calculation for problem with distributed mass, and it is not it's very time consuming, and it is not advisable. But the idea is, in the first example I have shown you how to use some assumption to make the model ideal to a problem which can be solved analytically. Through that you have learned how to do the model verification, like how to do numerical modeling and how to verify it. And here of course we cannot compare with analytical solution, but we can get some idea of different modes, right? Different mode shapes and corresponding frequencies. From the frequencies you can understand this the high frequency modes. So this will not occur very usually. Of course the first mode you can observe very naturally. Second mode, yes, but the higher modes the frequencies are quite high. Okay, that's all for now. Thank you.